Hi, I'm Merce Marti again, and welcome to this second lecture that I'm giving in the Machine Learning School in Seville, online this time. Today we're going to talk about some predictions techniques in machine learning. Probably from the previous session I did, you remember that we built the first ML model and we predicted from it. But now today we'll see that we can do more with our models than the basic default prediction that we did, and how we can improve the way that we build these predictions. So remember that we used some training data, created a model from it that had some rules, some patterns, and from that we want to use these patterns to predict in different ways in order to improve the results, right? So that would be how to operate the model. The model is there, is the same, has learned the patterns, has learned the rules, but doing different actions, we can change the way that model is used. And to remember what we did, we had been using data about some people that asked for loans. Some of them were returned and some they weren't. And finally, there was a field in our dataset which is called serious delinquency in 2 years. That was the thing that we wanted to predict. We had some examples where people were delinquent or not, and we built a model that found out some patterns, some conditions that made that some groups of people were more prone to be a serious delinquent in 2 years. When using this model, what we saw is that we could use a form to input the information we have about a new customer that wants a loan, and see whether he belongs into one of these groups, follows one of these patterns, that finally ends up in people mostly not returning their loans. But that means only that the group of people where that new customer falls in is mostly for that, right? It's the most probable outcome in that case has been so far that people are serious delinquents in 2 years, and that's what this screen reflects. Here you can see that given some conditions for the new customer, previously customers like him or her were 67.94% not returning their loans, so being a serious delinquent in 2 years. And even if not everybody behaved the same way, as this is the most probable outcome, that's what the model predicts by default, right? But what if we used the same rules, the same patterns, so the same model, and instead we decided to return a prediction in a different way, and we only accepted the prediction if the result is over a certain, a concrete probability threshold. In the image you can see that we just set a different selection of criteria, and we ask for the class serious delinquency in 2 years being 1, so the ones that didn't return their loans, and only if the model predicts that using a probability over 70%. If that's the case, we will predict that we have a serious delinquent. But if not, if the probability is below that 70%, then we would still consider that this customer will probably return his loan. And in this case, of course, as you see, the prediction changes, because in our case, the probability doesn't reach that threshold. So the prediction now that we have set a different set of conditions, even if the model is the same and has the same rules, has changed. What does it mean? Well, it means that when you use such models, you will need to reevaluate what you've done. You remember that in our previous demo, we saw that when you use the predictions by default for the model, the results of the evaluation, this confusion matrix, were the ones that you have in the top of the image, where only 422 instances of the test set were really predicted as people that were serious delinquents right. And you can try to increase the recall, just like we did before, by doing some balancing in the model, without changing the rules of the model, only changing the operating point, the way we operate that model. And that means setting a threshold, a probability threshold of 20%. If we set that threshold and you try to do the same and evaluate, you would see that the predictions that are of people that are really serious delinquents in 2 years will increase. And the ones that will really match what happened in reality will also increase to 1004. So without changing the model, without retraining, without adding more data, just by changing this lever, we've been able to change our predictions and to increase our recall. That is the thing that we wanted to do. So if you want to have a look at how you can do that using the platform in a real case, remember that we had this evaluation. This was the evaluation that we had for the first raw model that was doing predictions. As you see, the predictions that are really matching people that are serious delinquencies are 422, as I said previously. Well, you can operate differently on that model and create different evaluations from it. If you click on that button here, you will see that the screen is just enabled with more controls, and you can select, as we did before, the class we are interested in, which is the people that is a serious delinquent in 2 years or will be a serious delinquent in 2 years, and also act on this slider here, which is setting the threshold of probability where we will accept that prediction. And in this case is set by default at 50%, which is more or less, it's the same as using this criteria of the majority wins, right? And instead, you can change it if you want. You can act on that slider and move it backwards till you see that as you move the slider, the evaluation measures, in particular the recall, are changing. So if I'm 50%, my recall is around 21%, and if I go for 20%, my recall increases till 50%. Of course, when I do that, my precision is worse than before, because I am predicting people that return their loans and people that will not return their loans. Finally, what you want is have like a trade-off between the recall that you want to increase and the precision that you're losing. And this means finding the best point in this curve here. This curve here, as you see, this point here is the point where we are. The graphic is depicting the number of the true positive rate, so how many true positives are found over the total, against the false positive rate, so how the percentage of false positives over total. And what you want is, of course, to increase the true positive rate as much as possible by maintaining a low false positive rate as much as possible. So you would like something in the top left corner of this graphic here. If you move the slider, you will see that the point in the curve is also moving. Sorry about here. If you move the slider, now. If you move the slider, then you will see that the point moves along the curve also, right? And what you do is selecting this probability threshold, so you're moving along these different operating points for the model. That's what you do, and try to find the one that optimizes your cost in reality. And in this case, it might be this 20% I was talking about before. So that's what you can do to operate differently with the model to increase whatever you are, the success rate of whatever you are predicting, right? Also, this is only applicable to the supervised learning problems of classification problems. But talking about different kinds of models, like unsupervised models, we can have a look at what we do in clustering by default. What clustering does is trying to find out the groups of data that are similar between themselves and different from the others, so that you can do some segmentation of the data that you have based on the properties that you are providing, right? And once you have a cluster, you have built a cluster, the prediction that this cluster is giving you, given a new case or a bunch of new cases, is to what group do they belong. That's a kind of new label, right? The cluster has found some structure in your data, has labeled each of the groups, and when new information or the same information needs this additional tag, this additional label, you just run it through the cluster and add this information as a new label in your data set. That's what we are going to do in the platform in a minute. But you need to be aware of one thing. Clusters work by looking for distances between the different properties that you have in your dataset. So when you have a numeric field, distances are computed like some scaled Euclidean regular distances, right? But if the new case that you are going to run through a cluster to obtain a label, a centroid in this case, which is the center of each of these groups, misses some numerical information, some numerical field, then the computation to find out which is the centroid that corresponds to that new case will not work, because you cannot compute the distance to an empty field. So you need to be careful about that, and if you have data that is not complete and has some missing numerical fields, then you have to choose what's the more logical alternative. So you can put, for instance, that by default, that missing information is filled with the mean or the median or a zero. And that's what we'll do with another data set here. I have previously built a cluster model for Airbnb data. This data contains some apartments that were offered in Amsterdam by Airbnb, and it has the information about the description of the apartments, of course. Here you can see some words that belong to the description of the apartments, and also the number of baths. You see that mostly they have one of them, but there's statistics about how many are on top. They are 8, and the number of rooms and the price they are rented at. So just based on that data, we try to do some segmentation, and just by default try to find out how many groups and what do they contain. And as you see, for instance, here you have small groups where the number of baths is a little bit more than 1, so it's probably 1 or 2, and the number of rooms is over 3 or around 3, and the price is higher. It's a small number of selected flats, and here there are smaller flats which are more common in Amsterdam, so they have probably 1 bath only and 1 room only, and the price is fairly lower, right? But if you have that and you want to, for instance, offer an alternative to a customer who is in the range of the things that he has already rented, maybe you want to assign a label to know for that customer what's the kind of flat that would work, right? So you would like to have the ability to add a new column where you can tell what's the kind of segmentation group of cluster that corresponds to each of the flats that you want to use or to give to a customer. And that can be done not by using single predictions, because you won't be filling in the information for each of the flats, but doing a batch prediction. I just upload the information in BigML, create a source and a dataset as I did with my first BigML model, for instance, and from that I can create a batch centroid. But as I said, I need to be careful, because maybe some of my data has missings. And if I look at my data here, I can probably see whether it happens or not. And I find out that there's 25 cases here where there's a missing in the baths field, which is a numeric field. As I said, if I try to predict for that, I will not be able, the algorithm will not be able to compute which is the cluster that where that instance that has a missing belongs to, right? So finally what you need to do is to fill in somehow this information by default. And when you do that, you're able to do the prediction. So let's try to do it here. Again, let me get the cluster, create a batch, create a batch centroid, but using the configuration tool so that we can input. With the configuration tool so that we can input also the information about what I want to put by default when I find a missing. I choose the same dataset because I want to assign a new label to that same dataset to store the information about which cluster does each row belong to. And here in the configuration section, I can choose to say, well, if I have no information beforehand about a missing field, then I will use the mean of the entire field to be assigned as a value, so that we can compute these distances and know which is the cluster that it belongs to. And when I do that, I just run through the different computations of distance till I found out which are the clusters that they belong to, and I can create a new data set where on top of the information that I have originally, I have a new field, which is this cluster field here at the end, that has 4 categories, as they were 4 groups, 4 segments of clusters, and each one of them, each one of the rows in my dataset has been tagged with this new label, the cluster 1 or 2 or 3. We could change the number, of course, and maybe the flats that are more expensive, we can say that they are more exclusive, or the majority that are smaller, we can say that they are regular flats. So these kind of labels are telling us what's the segment of objects that we are dealing with, right? This is the kind of predictions that the clustering will give us. Another kind of model and another kind of prediction, of course, is detecting anomalies. If you want to detect anomalies, you want to find out what is different from the rest of information in your dataset, right? You want to detect what is easily separable from your dataset. And this is done by analyzing the differences between each of the properties that you provide in your dataset. And based on that, and based on if they are similar or not to the rest, an anomaly score, so a number that ranges from 0 to 1, being 0 very normal and 1 totally anomalous, is assigned to each row. Every row is assigned a new tag, again a new label, which is the anomaly score that is telling whether it is or not very strange, right? And this is important not only to find out fraud, for instance, or to find out the outliers, but it's also important when you want to do supervised learning in a classification case, because you will be probably able to remove some of the anomalies first in your dataset before building a regular supervised learning model. And that could improve the generalization of other models, because sometimes these instances that are outliers, that are things that are not regular, will just spoil the process by which the model generalizes. And either if they are errors or if they are very strange things that happen sometimes, probably that's not the general rule in your model, and what you want for your model is to generalize well. So that would be a good idea. And let's also do an example of that. I have here a data set which has information about patients that might or might not have diabetes. Here you can see that there are some fields: the pregnancies, the plasma glucose, the blood pressure, the insulin level, the BMI, the anticipated age, and finally a field which tells us whether these patients had or not diabetes. So a doctor went here and just as an expert gave this label to that field. So we would like to build a model, and we will go and create a decision tree or an ensemble or something. But before that, let us have a look at it and see if there are some anomalies that we can remove from the file in order to do this learning better. And if you create an anomaly detector from that, you will see that finally this anomaly detector gives you the 10 top most anomalous rows, and we will be showing us which are the causes for this anomaly, which fields are causing the difference between these rows and the rest of the information in the data set. And here it is. You see that on the left, you see the list of top anomalies, and the anomaly score, which is that figure here, 63.01, for instance, is the anomaly score for the first rule. And here below, you can see which are the fields that are different from the rest and which is the percentage in which they contribute. So the field that contributes most to this difference is insulin in this case. The following one is diabetes pedigree, and the third one will be plasma glucose. And the values are here in orange, just painted in orange against the rest of the distribution of values for the rest of rows in your data set. Here you can see that the insulin is very high. The diabetes pedigree is also high. The plasma glucose, which is strongly related to the fact that someone has diabetes, is also very high. But in this case, the patient did not have diabetes. And that is something that is not normal. So either this is a very lucky person, or this is an error when someone just filled in the form for him. So in one way or the other, the best thing we can do in order to create a decision tree model or supervised learning model is removing that kind of anomaly. And typically, everything which has an anomaly score over 0.6, more or less, will be considered an anomaly. So I can remove these two, the ones that over 0.6, create a new data set from it. And the data that I would have now, it's like clean data. The outliers would have been removed, and then we could start making supervised learning models from it, and it would probably give us better evaluations than the ones that we built before, right? So it's a good practice also checking first if we can remove some of the anomalies before start making these supervised learning models. And the third case of unsupervised learning prediction that I wanted to show you today is the case of associations. Associations are a bit particular because when you are trying to find out an association, what you try to find is things that happen together more than often. So think of the market basket analysis. If you were to analyze what products are bought together more often than it would be expected if you were filling your basket at random with the products in a supermarket, then some of the products would go together more often than it would be expected, right? And that's the kind of thing that association discovery finds out in your data. For instance, if you were analyzing supermarket market analysis, it would find out some rules which have high lift. It means that the proportion of times they appear is higher than the ones that would correspond if you chose by random. But that the lift is also associated to things that are not bought very often. So there are things that are not so common, but they have a strong relation one with the other. And the example is maybe caviar and vodka, right? If you are buying caviar, probably you're also buying vodka. So you will see in a basket, if you find one of them in a basket, you will probably find out the other two. And that's the kind of rules that we can find out in associations. And now we will have another example of what associations can we find in some data. And this data will be an excerpt of a file dealing with information about the COVID-19. We found the original file is in one of the published repos from Kaggle. That's an excerpt and has some transformations in it, so please don't take it into account for research. It's something for demo purposes, and you can, if you want to use something for research, you can just go to the source, which is described here, and you can find this file too in the gallery, in our datasets gallery, which is here, and where you can find datasets also with examples of other kinds of data to play with. So if you want to look for it, you can just search it here, COVID-19, or if you want to look for other health related data, you can also select here the health category, and you will find more datasets to play with. But let's use that Excel for now, and here, as you can see, there are the number of cases that you can find in a country, a summary of some of the things or the symptoms, or well, whatever information they find relevant related to the illness, the location, the country, the gender of people, the age, whether they were visiting Wuhan or they were from Wuhan, the symptoms they had, whether they recovered or whether they died. So if I try to see what's in here, and I try to find something relevant related to the fact that someone recovers, let's see if there's something that tells us what do the people that recover share more often than not. I can try to find out here rules that have a high lift. I would not ask for so many rules. I will just ask for 10 rules. And what I'll do is I'll ask only for the rules that are related to the fact of recovering, right? So I want rules related to the fact that the recovered field has a yes. Okay? So when I do that, I can create an association and see if there are some other things, some other properties that are related to the patients that recovered, right? And I here can see that, well, in this case, some rules appear. There's a first rule that apparently in Malaysia there were a lot of recovered people, 5.6 times more than expected by the rest of data. Also in Singapore, something similar happened with 4.5 as the multiplicative factor. But see that rule here at the bottom of it, there's a rule that tells us, well, if the cases in the country are below 8, then there's also the probability of recovering, the occurrence of recovery is doubled. So it looks like something related to the control of cases is highly influenced or has a tight relation with the fact that people recover. Of course, you need to think that this is a partial file that has stated cases, so maybe Malaysia was having by the time the data was fed into this file, Malaysia had a longer evolution than the rest of countries maybe, and the cases of recovery started to show out there, and in other countries were still in hospitals. So it's not something, I mean, you cannot just blindly learn that, it looks like if we want to cure COVID-19, we just take a flight to Malaysia, right? You need to think over what this data means and what's the time span in which this data has been taken and how many cases were in each of the situations. But still, you see that there are some rules here that can tell you, can give you some sense of what can we find out, or what information can help us then build some other type of models that can be useful to stop that illness, right? And if you want to do the same again, but instead of having the recovery, the recovered patients into account, we can try to find out if something is related to the people dying. And if we do that and say that we want to find out rules that have to do with the deaths instead of the recovery, we can create a different association, selecting the other consequence, and again is looking for things that could occur when someone is dying from that disease. And the rules that appear here Well, of course, if the summary includes that, that's just about data. But you see that if people is from China and the age is over 60, 5.8, well, there's 70 times more chances to have this final ending, right? So finally, this kind of relations, even if that is not a supervised learning model that we could try to do, because we have a field, which is the dev field or the recovered field, that has a content and has some examples that we can learn from. There are a few examples against the total number of examples that are provided in the dataset. So when there's this great imbalance between the data that is interesting for us and the total data in the dataset, sometimes associations can help us learn which are the things that are related somehow, not maybe causally, but that could occur with the result that we are trying to predict. And of course, these are some examples, but you could find out that each of the different models that we can build, either in supervised or unsupervised learning, can provide examples of labels that can be assigned to your information, either to improve it or to just be taken into account to decide, to take action from that. In classification, we'll assign a label to an objective field, to something that was previously known in historical cases, like will this candidate meet the requirements? And in regression is like in classification, but for a number, for a numeric field. Time series forecasting will give you this projection, but all over time in a coordinate, in a future temporal coordinate. Cluster analysis, as we saw, will provide new labels telling us which are the groups that every row belongs to. And anomaly detection, these kind of scores that tells us whether something is more or less anomalous, and association discovery, this kind of feeling of relations between different properties in your dataset. So now we've seen that we can create models, this part in the middle, that we can operate with them and obtain these predictions from them. Of course, there's previously a lot of work, 90% of the work, which is in preparing and transforming the data. And probably we would think this is an iterative process in order to improve the results, of course. But probably we could think, well, that's it, right? I mean, we have learned how to build our data. We need to improve. We do predictions. We see if it's good enough. If not, we come back and transform again. That's what I should do. And that's only what I should do, you know? We shouldn't do anything else. It's not really true, because once you have a performance model, something that seems to solve your problem, you will need to bring it to production. And bring it to production means different things depending on the different scenarios that you can have in your business or in your research group. One scenario could be, I am in a call center, I receive one call at a time, and I want to know if the person who's calling will churn. And of course, the operator will ask for data, and while talking to the customer, then will fill in a form and has time to see if this form is remotely responding and tell the prediction that the model gives us. That would be a single prediction like the ones we did in the previous session. I just filled in the form and I received immediately a prediction telling me what's the most probable outcome that the model gave me, right? And this is perfectly okay. But maybe you're not in that scenario, you're in a different one. You're in a supermarket and you want to know sales, and thus you want to periodically predict a high amount of data, not only one. You would not fill the form once and again, but you would instead upload a bunch of data, create a data set with it, run it through the model, and then obtain back another data set, something that you can download, for instance, in your company weekly, hourly, daily, and fill in your information systems with it, right? And that would be a batch prediction, the one that we have also done using the cluster when we create the batch centroids, labels assigned to each of the rows. This will create one prediction assigned for each of the rows that we provided first. There's a third scenario that you can have. Maybe you're in an industrial chain and you want to know if one of your processes fails and control it immediately, of course, to stop the production at that point. In this case, you will probably have sensors controlling what's happening there, the current, the voltage, whatever physical property you think it's important. And based on that, the model will be able to predict whether the production will fail or not. But you want to do it on the spot because you want some quickness, right? That would probably qualify for what we call local single prediction. So you would not want someone to fill in a form in a remote place and wait for the latencies so that the information goes back to you. You want that the model, the patterns, can be downloaded to your tablet or your hardware, even in your machine, and then executed in some kind of language that is able to understand these patterns and produce the results immediately, right? And a different scenario, but also related to that, is if you were doing online legal assistance and you have a website and you wanted to provide a service to the customer where the customer uploaded a collection of documents and your website would tell you whether you should sign them or not. And this would mean that you would not only do one prediction but many at the same time. But you also want to be quick, so you want to do it on the website. You don't want to have to wait to do it in a weekly or daily process. So that would mean, for instance, doing a loop and doing local batch predictions, again in different gadgets, in different machines on your website. So going to production is something different for depending on the point of view of the user. Of course, when you train models, you need the flexibility and the capacities, the scalability of some platform that is strong enough and flexible enough so that it can ingest the quantities of data that you will need to use to create the models. But once you do predictions, usually predictions have a very lower requirements. I mean, you don't need the power of CPUs or memory to do the predictions of a decision tree model. It's very easy to follow a chain of if-then conditions until you find out which is the prediction. So you can decide whether this part, the part of making predictions, can be done remotely by the same machines that did the training or locally. BigML, of course, offers this white box model that allows you to download your models to your machines, to your gadgets, where you can, using some language, run these predictions with no connection whatsoever to the server that created the models. And in this case, you can see here two examples, one in Python, another one in Node.js, of how you would do that. Of course, we provide some libraries that can be used in those languages to interpret the models, the patterns that we create in our servers. And that's what this code does. This code just uses a class which is called model or local model to download this information from BigML, put it in your computer, and then from there you can just execute a prediction with even if the model in BigML has been deleted. So you don't need to keep something remotely to use this information locally. You just store it in your local file system and it works from there. And finally, remember that this model that took so much effort to create, it's not something probably that will stay there forever because data is evolving. So at one point or another, probably you should ask yourself whether this model is still valid, and you will probably have a need to retrain it. Then if you think about a machine learning project, you think about something that has some life and that needs, of course, of model integration. So not only training the model, but also connecting that model to the inputs that you receive, the inputs of information that we receive every now and then from your business, and give the results to the outputs that you will use to take decisions from. So the prediction should be connected to the rest of your system so that you can take action based on that prediction. And also, as time goes by, data probably will change, and you have to be monitoring the shift of this data and decide which are the conditions that ask for the model to be retrained when that data shifts. And finally, even you can be in the position of correcting that prediction, so the humans can help in that learning system by correcting predictions and feeding back this information to a new model that is able to improve the performance of the first one. And that's all for this session. I hope you enjoyed the predictions part. And if you need to make some questions, remember that we'll be in the channels to help you. So thank you very much for your attention.